Hello, my name is Leo, and today we will be discussing and deriving the Euler-Lagrange equation. The Euler-Lagrange equation is the bread and butter of a subfield of mathematics called the calculus of variations, which I will give a brief introduction to in this video. You may have heard of something called the principle of least action in classical mechanics. As you know from your introductory track courses, the trajectory of an object is given by some path or curve in space and time, and is therefore a function of space and time. This principle of least action takes the mechanical energy of any given system and manipulates it in just the right way. That way it gives us the path, the trajectory traversed by any given system that minimizes this energy. This is where you may have heard the joke that nature is lazy. So I'll stop talking about its applications, as it may hinder your understanding of the topic so far. So I'll come back to it at the end of the video. Leonhard Euler, whom I'm sure you're all familiar, was arguably one of the most successful and brilliant mathematicians to live, and most definitely the most prevalent of his time. In the mid-18th century, he started to formulate his ideas of the calculus of variations. And fast forward to the year 1755, a bright-eyed young mathematician and astronomer, Joseph Louis Lagrange, at the age of 19 years old, reached out to Leonhard Euler, expressing that he has his own methods on the calculus of variations. And Euler was so impressed with this young man and his insights that he stopped what he was doing to expand on these ideas of Lagrange's. And throughout the late 18th century, Euler and Lagrange worked together to develop and refine the calculus of variations. And in 1788, Lagrange published his Mécanique analytique that provided a new revolutionary formulation of classical mechanics, the formulation we refer to today as the Lagrangian formalism, Lagrangian mechanics. So, without any further ado, let's get into it. We'll start off by covering the calculus of variations. And before we do so, let's review ordinary calculus. Within ordinary calculus, we're used to working with and manipulating functions. And these functions are of variables, whether single or several variables. The calculus of variations is not much different. Here, instead of dealing with functions, we're dealing with something called functionals. And put simply, a functional is simply a function not of other variables, but of other functions. So, when we deal with optimization problems in our introductory calculus, we know that we take the derivatives, whether it's the first or second order derivatives of a function, and set it equal to 0 to find the points of the function where the slope is 0, and we classify them. In terms of the calculus of variations, we can also find these extrema, but not of the functions, of these functionals. And instead of a point that is we're trying to optimize, we're optimizing functions. And we'll refer to the optimization
of these functionals, analogous with the optimization of functions as stationary points. Now this can be a little confusing at first because it perfectly makes sense to call the points where the slope is 0 on the function for regular calculus, but conceptually, for the calculus of variations, we're not finding a point that optimizes the function, we're finding a curve that optimizes a functional, and we'll see what that means in just a little bit. But we can refer to both the point and the function that optimizes functions and functionals as the stationary points. We begin with a problem. This problem, I will try to make as intuitive as possible, is we have 2 points, A and B. A and B. Here we have the x coordinate x1 and x2, and here we have y1 and y2. And we have some function, some curve that connects the two from point A to B. And let's say we wanted to find out total length of this curve from point A to point B. Well, what we can do is we could take tiny infinitesimal chunks of this curve and add them all together, and that would look as the total length S of this curve from A to B would be taking a tiny length ds and summing up all the ds's from point A to point B. Yes. And we can go ahead and look a little closer, and we can rewrite ds if we zoom in a little bit. ds, well, if this is our tiny infinitesimal length ds, then we could break it down into our components dx and dy, and go ahead and write ds in terms of them. Using Pythagorean theorem, that's simply dx squared plus dy squared taken to its root. So, when we rewrite this integral from A to B of dx squared plus dy squared, we can go ahead and factor out the independent variable dx squared. That way we can write this integral in terms of dx, and when we do so, we get the integral of 1 plus dy squared over dx squared dx. And we're integrating in terms of x from x1 to x2. So, let us clean this up a little bit and write that total length of the curve from point A to point B is simply the integral from x1 to x2 of the square root of 1 plus y prime squared dx. Now we've came up with a formula to find the length of any curve connecting from point A to point B. And let's say we wanted to find the most efficient path from point A to point B. We wanted to minimize the distance from point A to B, an optimization problem. As we're familiar, we know from experience that the shortest distance between 2 points is the straight line distance between them. So, if we were to write this straight line, in this case, the line segment from point A to point B, we know that's going to be some function y in the form of mx plus b. Some constant, the slope m, plus another constant, its y-intercept. In this case, there is no y-intercept, but nonetheless, some function in the form as such from the domain of x being between x1 and x2. Now, let us rewrite the length of this curve as the integral from x1 to x2 of some function of the function y of x. In other words, a functional of y of x, its derivatives, y prime of x, in this case, just its first order derivative, and it's a function of y of x's independent variable x with respect to x. To transform this into the problem of the calculus of variations, we're asking what function y of x, when plugged into this functional, when evaluated, will give us the minimum distance between point A and B. So, to make it more intuitive, we already know the solution. The solution is here, y equals mx plus b in the from x1 to x2. So just to prove that, just for my own sake, let's go ahead and find y prime of this function. We know that y prime, the derivative of y with respect to x, is simply the slope m. And we could go ahead and rewrite that as y2 minus y1 over x2 minus x1. And when we plug that into this integral, we get that the integral from x1 to x2 of the square root of 1 plus this quantity, y prime squared, we get y2 minus y1 quantity squared over x2 minus x1 quantity squared dx. Well, when we evaluate this integral, we realize that the integrand is not a function of x. So it's a pretty simple integral to evaluate from x2 to x1. More simpler than I anticipated. It's going to be root 1 plus y2 minus y1 squared over x2 minus x1 squared times x evaluated from x1 to x2. And when we plug these limits in, we get, what do we get? We get root 1 plus y2 minus y1 squared over x2 minus x1 squared times x2 minus x1. We can go ahead and rewrite this by putting the x2 minus x1 within the square root, and we see that when we do that, this can be written as x2 minus x1 squared plus y2 minus y1 squared. And would you look at that? That's our distance formula, the straight line distance from point A to B. So as we can see, we've taken a functional and optimized it to find the function that minimizes or maximizes whatever problem we're looking to solve. And this is the goal, is to find some procedure to solve for the function that maximizes or minimizes a given functional. In this case, the curve connecting 2 points. Now that we are equipped conceptually with the problem at hand, finding a function which optimizes a given functional, we can start to derive that procedure in finding such a function. So, going back to the problem we just solved, 2 points, A and B, we found that the solution of the minimum length, the shortest path distance from A to B, is the straight line segment connecting the two, which we'll call y of x. And in finding the total distance from A to B of any arbitrary function, it was the integral from x1 to x2 of some function of functions y of x, y prime of x, and the independent variable x, dx. And I have done you a disservice by calling this a functional, when in reality, the functional this whole time was the distance s. Why? Well, concerning the optimization of the path concerned, in this case, the minimum path from point A to B, we wanted to solve for what y of x, when plugged into this functional, gives us the shortest distance from A to B. The integrand in itself is not a functional, it is a function of any particular y of x we choose to put in. Now we know we could represent any distance for any curve as the integral from x1 to x2 of some function of y of x, its derivative, and x dx, And now we can go ahead and come up with a function that represents any and all curves from point A to B. Could be this curve, could be this curve, it doesn't matter. An infinite amount of possibilities. We could go ahead and represent all functions connecting A to B as y bar of x. And we can write it as y of x plus some extra distance, wherever it may be. We'll call that extra distance eta of x. And you can see that this curve, any curve, y bar of x, no matter how small this variation of the solution y of x is, no matter how small this eta of x is, it's not going to give us the solution y of x. So we can exploit this idea by introducing a parameter alpha in front of the eta of x. And we just transformed this problem into an introductory calculus optimization problem, where we could now represent a functional in terms of this parameter alpha, the integral from x1 to x2 of some function of now y bar of x, any number of its derivatives, y bar prime of x, x dx. Where when now we know when alpha varies by nothing, when we set alpha equal to 0, there is no variation in our function y of x. It yields us our solution y of x. We can now take the derivative of s with respect to alpha, evaluated when alpha is 0, to yield us our solution to the functional that optimizes this functional. Okay, so we need to take the derivative of this functional with respect to alpha and set it equal to 0. And when we evaluate it for when alpha equals 0, it will give us the solution, the most optimum function for this given optimization problem. And when we do so, we get d alpha of the integral x1 to x2 of this function we set equal to 0. In order to simplify this, we have to use something called Leibniz's integration rule. Which states that when we take the derivative of an integral whose limits are constants and do not depend on the variable we are integrating with respect to, in this case, x1 and x2 are not functions of x. They are indeed constants. We can go ahead and say this is equivalent to taking the derivative, putting it into the integrand, converting it into the partial derivative with respect to alpha of this function, setting it equal to 0. So the integral from x1 to x2 of the partial of f with respect to alpha setting it equal to 0. So let me clean up the board and we'll continue the derivation. Okay, we can go ahead and use the chain rule and simplify even further. We have the integral from x1 to x2 of del f del y bar dy bar d alpha plus del f del y bar prime dy bar prime d alpha plus del f del x dx d alpha dx set equal to 0. Now, we have to take the partial of f. It doesn't seem we could simplify those, but we can find the derivatives of y bar and y bar prime of x with respect to alpha. And we can also see that when we take the derivative of x with respect to alpha, x doesn't depend on alpha. X is not a function of alpha. That term just goes straight to 0. Now all we have to do is find the derivatives of these functions. We can see that from our expression of y bar of x as we defined it, as it equals y of x plus the parameter alpha eta of x, when we take the derivative of y bar of x with respect to x, we simply get y prime of x plus alpha eta prime of x. And when we plug that in, this simplifies to the integral of x1 to x2 of del f del y bar. The derivative of y bar of x with respect to alpha is simply eta of x. Del f del y bar prime of x. And the derivative of y bar prime of x with respect to alpha is simply eta prime of x dx set equal to 0. In order to get use of the form that we have just derived over here, we want to represent this integrand in terms of eta of x, not eta of x and its derivatives. So the way we can do this is we can split this up into two integrals and just focus on the problem we have over here. And we can go ahead and perform integration by parts, because if we set eta prime of x to dv, once we integrate that, it'll cancel out the prime, and we'll just have it in terms of eta of x. So let's go ahead and do that. We could write this as the integral from x1 to x2, partial f, partial y bar, eta of x dx, plus the integral from x1 to x2, partial f, partial y bar prime, eta prime
of x dx set equal to 0.
I'll go ahead and clean up the board, that way we can go ahead and perform this integration by parts. Okay, just in case we've forgotten, the integral of u dv is equivalent to uv minus the integral of v du. And we wanted to set dv equal to eta prime of x dx. That way when we perform the integration, we get eta prime of x to eta of x. We have it in terms of eta of x. It cancels out the prime. So we can set dv to eta prime of x dx. When we perform the integration, we get v equals nothing but eta of x, just as we wanted. We have our u equal to del f del y bar prime, and our derivative of u with respect to x is nothing but dx of partial f partial y bar prime. So we can get that du is simply this quantity times dx. And now we could rewrite this integral. So we get the integral of x1 to x2 partial f partial y bar eta of x dx plus we have u times v. U is partial f partial y bar prime. V is eta of x. And this is evaluated from x1 to x2 minus the integral from x1 to x2 of v, which is eta of x, du. And du was given by this. Set all this equal to 0. Now, when we evaluate this from x1 to x2, we get partial f partial y bar prime eta of x2 minus partial f partial y bar prime eta of x1. Now, let's go back to the beginning of the derivation. So, connecting points A and B, the solution to the problem was y of x, the straight line distance from A to B. And we wrote down the function y bar of x in terms of any possible curve connecting points A to B. Now, the one thing that stays the same for all the curves y bar of x is that they all start at A and end at B. So we're given conditions that eta of x1 and eta of x2 is 0. There is no variation in the function at the points A and B. They are always stagnant. So we can immediately see that this term goes to 0. And we can go ahead and write this as the integral x from x1 to x2 partial f partial y bar eta of x dx minus the integral from x1 to x2 eta of x derivative of x of partial f partial y bar prime dx equals to 0. Now we could go ahead and combine these into one integral, which we can write as the integral from x1 to x2 of partial f partial y bar eta of x minus eta of x d dx of partial f partial y bar prime dx equals 0. Let's go ahead and clean up a bit, and we're almost done. Now that we have succeeded in representing this integral in terms of eta of x and not of its derivatives, we can go ahead and factor out that eta of x. So the integral from x1 to x2 of eta of x times partial f partial y bar minus d dx partial f partial y bar prime dx equals 0. This condition holds for any arbitrary eta of x we choose, and assuming that this function and this function are continuous, then this expression here must be equal to 0. Partial f partial y prime minus d dx partial f partial y bar prime is equal to 0. And this concludes our derivation of the Euler-Lagrange equation. Now that we've derived the Euler-Lagrange equation, let us take a closer look at it. Given any functional s, we can find the stationary point of this functional by solving the Euler-Lagrange equation and deriving differential equations in terms of this function that we could then solve for this function. Let's look at the Euler-Lagrange equation in its general form. The Euler-Lagrange equation in this form allows us to solve for the equations of motion for any given system. Lagrange defined a function L, the Lagrangian, the kinetic energy minus the potential energy of a given system. The kinetic energy is in terms of the velocity of the system, and the potential energy in terms of its position. So the Lagrangian is a function of both the velocity, the position, and time component, as t is the independent variable corresponding to the velocity and position. Lagrange found that the path traversed by every system is the one which minimizes the action. This takes us back to the principle of least action, where we can now define the action as a functional that's in terms of the Lagrangian, as the integral from time 1 to time 2
of the Lagrangian dt. This principle of least action states that the path or function traveled by the system is the stationary point of this functional we call the action. Here we see the q dot and q taking the place as the generalized coordinates, where q can be x, y, z, or r, theta, phi. Any coordinate system we choose will work just fine with this Lagrangian formulation. And so we have the terms q dot taking the place as the generalized velocity of the system, and q as the generalized position coordinate. Now this means as long as we have the position and the velocity of any given system, we can easily find its corresponding kinetic and potential energies, solve for the partial derivatives of the Lagrangian with respect to the velocity and the position, and in turn we get a differential equation whose solution is the path followed that minimizes the action. This idea of finding the stationary points of given functionals is not just limited in its application to classical mechanics, but is an indispensable tool used throughout many areas of theoretical physics. We can use it to derive Maxwell's equations and other field equations in classical field theory by treating the fields as functions that vary in space and time. The Lagrangian formalism led to the development of the Hamiltonian formalism of classical mechanics, which you may know is used throughout quantum mechanics. Even Einstein's field equations are derived using a variational approach. As for its applications and impact on society, that could be a video in and of itself, but just to name a few, we can thank the Lagrangian formalism and the Euler-Lagrange equations for the Industrial Revolution to make all those machinery and engines. It can be used to optimize electrical circuits to create more efficient and reliable technology, such as the smartphone or computer you're watching this on. Optimizing signals, such as signal processes and MRIs and CT scans for its medical applications, even optimizing the biomechanics of prosthetics. It can even be used to optimize models in economics and much, much more. I make this video now encouraging the viewer to go out and do their own study of the calculus of variations, the Euler-Lagrange equation, and the Lagrangian formalism of classical mechanics. There are many texts used to do so, and I'll list a few of them down in the comments section below. If you notice any mistakes or inaccuracies throughout the video, please do not hesitate to voice them down in the comment section below. I really hope you got something out of this video, and I'll go ahead and end things off with a quote from none other than Hamilton himself. Take care. The theoretical development of the laws of motion of bodies is a problem of such interest and importance that it has engaged the attention of all the most eminent mathematicians since the invention of dynamics as a mathematical science by Galileo, and especially since the wonderful extension which was given to that science by Newton. Among the successors of those illustrious men, Lagrange has perhaps done more than any other analyst to give extent and harmony to such deductive researches, by showing that the most varied consequences respecting the motions of systems of bodies may be derived from one radical formula. The beauty of the method so suiting the dignity of the results as to make of his great work a kind of scientific poem.